My name is Donghan Rou, and today I will present our work on the automated measurement of transimpedance amplifier using Infineon's PISOC 5LP microcontrollers. In this presentation, I will cover 5 key measurements performed to evaluate the performance of our TIA circuit: noise, bandwidth, stability, linearity, and lastly, dynamic range. The figure in the center of the slide shows the TIA circuit we implemented to sense current from a photodiode. Through extensive measurement analysis, we observed that increasing the feedback resistors improved gain, but degraded stability, bandwidth, and increased the noise. On the other hand, increasing the feedback capacitor improved noise and stability, but significantly limited the bandwidth. The main motivation for this work is rooted in the need for accurate waveform measurements in ATE-based electronic testing. Modern instruments such as digital storage oscilloscopes offer powerful features, but they are often underutilized due to their complexity. Misuse or misinterpretation, particularly of waveform metrics, can lead to misleading results. To solve this, we developed an ATE measurement system using Python, aiming to improve test accuracy, resolution, and efficiency. The TIA was implemented on an Infineon board, and our goal was to explore design trade-offs and identify optimal configuration for performance. To evaluate the TIA's noise characteristics, we shorted both the inverting and non-inverting inputs of the op-amp to ground and measured the output voltage for 1 second using an oscilloscope. We then performed an FFT analysis with a 1 GHz of sampling rate. A higher power spectrum density at low frequencies with a 10 dB decade slope indicated a flicker noise, followed by a flat thermal noise floor at higher frequencies. The noise amplitude followed a Gaussian distribution, as you can see in the figure below. Assuming an ideal op-amp with no intrinsic noise, the main contributor to output noise can be categorized into two. First one is thermal noise due to the resistors in feedback, which can be expressed by this equation. The second one is the shot noise and thermal noise due to the noisy photodiode current, which can be expressed by this equation. Combining both yields an expression showing that the total noise increases with RF and decreases with CF. The result showed that the higher powerful configuration, which had a greater bandwidth, showed higher RMS noise since it's intuiting over a wider frequency range. The RMS noise was lowest when we have RF of 250 kiloohms and CF of 4.6 picofarad. The next measurement we conducted is the bandwidth. We applied a sine wave voltage to an LED using an 8WG and measured the peak-to-peak output voltage from the TIA. As the input frequency increased, we recorded the peak-to-peak voltage to extract the bandwidth. The results combined that both RF and CF negatively affected the bandwidth. Interestingly, the measured transimpedance gains were constantly higher than the theoretical predictions. To test stability, we applied a 1 kHz scale wave to the LED with a 2.5 volts of offset and a 2.5 peak-to-peak signal. We captured the transient response of the output for 10 seconds of 1 kHz of sampling rate. The result showed higher RF increased the settling time. On the other hand, increasing CFs transitioned the response from underdamping to the overdamping. For the linearity and gain measurement, we applied the ramp signal to the LED using a digital multimeter. The slope of the output response depended only on the value of the feedback resistor, and CF had no effect on it. The maximum output voltage was clipped at 5 volts, limited by the power supply. As expected, higher RF resulted in a steeper slope than a lower RF. For the dynamic range measurement, we calculated dynamic range as the ratio of the maximum output voltage to the RMS noise voltage measured earlier. As a result, the configuration with the lowest noise also provided the highest dynamic range. Accurate bandwidth measurement was initially challenging due to strong flicker noise at low frequencies and ambient light interference affecting the photodiode's output. These environmental factors distorted the signal, especially in the low frequency range. To address this, we used the waveform averaging function of the oscilloscope, which effectively suppressed low frequency noise and allowed reliable extraction of peak-to-peak voltage. For future work, more precise evaluation of the TI's performance can be achieved by directly measuring the current through the feedback network to obtain accurate transimpedance gain. Measuring the supply current of the op-amp to better estimate overall power consumption of the circuit could also be done.